Which one is your presentation screen?
This one.
Oh, you've done this before. I don't need to tell what to do.
If normally I just close everything out to make sure there's nothing open that I want people to see accidentally. Up.
90 attendees waiting. Is your microphone?
It is on because I guess I'm the presenter, but you haven't broadcasted anything, right? So.
No, I'm actually I'm live right now, but you shouldn't be the presenter. It's going. No, not yet.
What I don't like about this mic is I don't know how to mute it. I'm too afraid of pressing the
You have audio controls?
button on.
No, do you have audio and microphone controls? Go to your audio center. Where's your sound panel? It should be a panel.
Nope, we got the noise again. left corner or by going to the View menu and clicking on the Hide Control Panel. You can also expand the panel by clicking the same button or using the View menu. Second, you have the ability to submit questions using the Questions pane located near the bottom of the control panel. If you're having difficulty listening to the audio, please just double check the volume on your speakers, or feel free to contact us using the chat or the questions window. So once again, thank you for joining us for today's technical webinar on electromagnetic transient program. So we'll go ahead and get started right away. Today's webinar will be focusing on performing EMTP studies after you have built your network model in ETAP. Traditionally, in order to perform EMTP studies, the network model needs to be recreated in EMTP software, which is very time-consuming and duplicated effort, having to rebuild the model all over again for studies such as ferroresonance or insulation coordination. So in today's technical demonstration, which we expect will last somewhere between 30 to 45 minutes, we'll be demonstrating an interface with EMTP-RV software that will allow you to tremendously reduce the engineering man-hours for EMTP studies by eliminating the need to manually recreate the electrical model again for fast transient analysis. So as a brief introduction, my name is Tanuj Khandelwal, VP Engineering Services at ETAP based in Irvine, California, and I'm pleased to be co-presenting this technical webinar with Emmanuel Rutovic from EMTP-RV, who's actually located in France. So we're coming at you from two different continents this morning. The 3-day event, which is the ETAP 2015 User Conference, is coming up April 20th to 22nd. If you haven't registered already, please feel free to visit our website, etap.com, User Conference 2015. This 3-day event includes applications of ETAP, user case studies, user presentations, technology demonstrations, and obviously the ability to network with other ETAP users. The call for presentations, the conference registration, as well as some exhibition opportunities are open. So once again, please feel free to visit our website and find out more about the ETAP 2015 user conference. For those of you who are new to ETAP, ETAP is basically the largest power system analysis software company with over 150 full-time employees worldwide and presence in over 75 different countries. These are some of the locations where you will find ETAP sales and support centers throughout the world. We also offer technical support, obviously for ETAP software that's available 24/7 online, as well as global phone technical support. If you are an existing ETAP user and you have not registered for a help desk account, please visit our website again and make sure you register for your free help desk account, where you can find a lot of frequently asked questions, as well as recordings of previous technical webinars that you may have missed in the past. These are some of the hours in green where phone support is available in your local time zone. The ETAP Regional Technical Support Centers are there to answer any questions about ETAP engineering software, and you can essentially contact us in any of these time zones within the hours specified. And as always, we continue to expand the reach and integrate additional technical support centers to this list. ETAP basically is a software that allows you to migrate all the way from simulation design analysis of your electrical system all the way into real-time operations. And because ETAP is extremely flexible, there are no limits on the number of components. You can essentially model networks from very small systems such as aircraft systems or shipboard systems all the way to large transmission and distribution systems. in a very easy, graphical, user-friendly manner. So as a result, we supply ETAP software to various industries such as low voltage markets, commercial facilities, hospitals, and so on and so forth. Generations such as thermal, nuclear, renewables, transportation such as railways, marine vessels, FPSOs, distribution systems such as citywide distribution networks, as well as oil and gas upstream distribution, transmission networks, which is essentially high voltage, extra high voltage, and industrial systems such as manufacturing, metal and mining, oil and gas, and so on and so forth. So these are essentially some of the main industries we supply ETAP software for simulation design analysis as well as optimization. The same network model, as I mentioned earlier, can be transitioned to ETAP real-time to give you a model-driven power management system. We have a new solution which is called ETAP Grid for transmission and distribution that allows you to model systems all the way from microgrids to smart grids. And another new solution for railway systems where you can essentially model the low voltage signaling system, size the conductors, do shock protection studies, as well as include the medium voltage traction system and solve the entire rail network, including the train performance calculations, all in one solution. So ETAP basically is a very comprehensive software with over 50 different modules that allow you to go all the way from design through construction, commissioning, all the way into operation and maintenance. So basically throughout the entire life cycle of the electrical system. The program essentially is nuclear certified, which means the software and the engineering libraries are verified and validated for nuclear use. We've had the nuclear QA program in place since 1991, which complies with 10 CFR 50 Appendix B, and these are some of the other standards that we comply with throughout the life cycle of the program. One last high-level mention about ETAP before we jump into the application itself. This is more of a 30,000-foot view of all the integrated foundations that are inside the program. Again, for those of you who are not familiar too much with the ETAP program, we essentially have a view for doing network analysis such as power flow, fault analysis, motor acceleration, transient stability, and so on. You can essentially model the electrical system using geospatial information, so we can extract data from any GIS system, bring the model inside ETAP, and then allow you to plan a geospatial network all within the same application. There's an integrated protection and coordination program that allows you to model or include the protected devices and perform protection as well as coordination studies. You can go down to the low voltage network and model the three-phase, single-phase panel systems, do cable sizing, shock protection, using various standards such as IEC, British Standard, IEEE, and so on. You can take the cables in the electrical diagram and create a cable routing such that you can see the effect of sidewall pressure and tension on the conductor as it's being pulled through a manhole. The same conductor can be put into a different view, such as an underground raceway view, where you can solve for steady state or transient temperature calculation using methods such as Near-McGrath or IEC 287, and understand the thermal or the temperatures inside an underground raceway system based on different ampacity levels or different amps. You can model substation ground grid and integrate it with ETAP, where the program can be used to calculate line to ground fault currents, and based on that you can inject that current into the grid and understand the step and touch potentials using IEEE and finite element method. You can also include dynamics inside ETAP, and these are essentially the electromechanical dynamics, which we'll be expanding upon a little bit more in this webinar. where you can model the transfer functions of various machinery such as generators, exciters, governors, power system stabilizers, and also use tools like dynamic parameter estimation to tune the time constants and gains of various control blocks. You can also use ETAP to go down into the control circuit diagram level, where you can model the control relays, Form C contacts, solenoids for control circuit diagrams, including the voltage drop calculation, such as a breaker, open-close circuit, a DC motor, stop-start circuit. These are some of the examples of control circuits you can model and simulate inside the program. As I mentioned, ETAP network model that you use for design and planning can be migrated over to a real-time system where the model is connected with the real-time data, and we run various advanced applications on that model, such as predictive simulation, intelligent or fast load shedding, various energy management functions, as well as microgrid controllers. The same information can be visualized using web applications such as your web browser. In fact, you can also even run certain scenarios directly from your web browser without actually having the ETAP application open, so it gives you a lot of flexibility. And the last foundation is data exchange, which we'll also be utilizing in this webinar, that allows us to migrate data from ETAP to other third-party applications, which can be a single unidirectional exchange, or it could be a data synchronization, which means bidirectional data exchange. So with that, I'll migrate over to the ETAP application itself and show you a little bit about the data modeling and dynamic calculations. And then once we complete the electromechanical types of studies, then we'll see how we can migrate this model into a different environment where we can essentially perform electromagnetic transient studies. So I'm going to move this diagram over a little bit. Again, for those of you who are not familiar with ETAP, I can build a network model fairly quickly by just dragging and dropping and connecting components together. So I just have a very simple utility transformer, let's say another bus, and we'll go ahead and connect a machine to the system as well. You can simply double-click on the component to access the property editor. So I'll go ahead and open up this transformer, specify, let's say, a voltage level in here, let's say about 3.3, and provide an MVA for this transformer. So the minute I click OK, what you'll see is the voltage is propagated throughout the network. Since I'm color coding based on voltage, you'll see the primary side and the secondary side have been color coded appropriately. And the next step for me would be to go ahead and specify some nameplate information for this piece of equipment. So I can go ahead and do that. And I essentially want 3 of these machines connected here, so I can change the quantity. And that's all it takes to simply build the network model inside ETAP, and I can go ahead and perform power flow calculations. Now, if you missed out some piece of information, you can always double-click on the error message and utilize typical or sample data wherever available in order to complete the data entry and perform the calculations. So there's an error check built in that makes sure that the calculation doesn't run with erroneous information. So this is pretty much how I would perform a power flow calculation. If I wanted to perform fault analysis, obviously we need to add additional information. So I need to come in here and specify the utility MVA short circuit, and then go ahead and fault this bus individually, or I can solve the entire system in one shot, and then go ahead and run the calculation for device duty. So If I'm using IEC standard, then I can essentially set up my options appropriately. If I'm using ANSI standard, then I can go ahead and run my device duty calculation and see the fault current calculations as well. So as you are essentially performing different types of calculations, you can start adding layers of information into the program. If I was adding protective device information, so I would essentially add the relay and the CT here, and then go ahead and specify location of a breaker, and then just quickly build the protection system in this manner. So I'm going to go back to the system that I have here, which is an IEEE 9-bus system that's already pre-done for me. I have some protection information here, and what I've also done is included information about the dynamics of the rotating machine. So in this case, I've specified a subtransient model for the synchronous generator, which is required for performing a transient calculation. I've specified the inertia of the entire shaft that includes the prime mover, the coupling gear, as well as the generator. I've specified the exciter information, and which is the control bus. In this case, the generator excitation is getting feedback from bus number 2. And I've also specified the governor information. In this case, the governor is actually in droop mode, and I'm just using a standard steam turbine governor, but you can always drop down the list and access the latest and greatest governor model types that are already pre-built inside the program. If any exciter, governor, or PSS does not exist inside this list, you can always choose the UDM option and build the transfer function yourself and include it in the simulation. So with that, I'll go ahead and switch over to the transient analysis mode, and this is essentially the electromechanical transient or the dynamic stability program. So I've gone ahead and defined inside my study case that I'm placing a fault on line number 3, and the fault happens to be at 50% down the length of the line. That means it's halfway down the transmission line. And I have certain protected devices here that I'm going to temporarily disable, so we can see what happens if there is a fault in the system and it is a sustained fault. That means the fault is essentially not cleared. So I'm going to go ahead and run the simulation here, and you can see how quickly the transient stability program finishes the calculation. You have a time slider with an action list that you can navigate through, and with every click you can see a different step in time and how the results are changing on the single line diagram. The same information you can visualize through a plot, so I can look at the relative angle and the speed, which I'm interested in this case. If I look at the relative power angle, you can clearly see that the system has become unstable. 2 of the machines have gone out of step. In fact, the third one is the reference machine, hence you will not see any angular shift, rotor angle shift for the third machine, because it's the reference, so it's at 0 degrees. But the other 2 machines are out of step in a few milliseconds after the fault is initiated. So we can look at the time at which the rotor angle essentially reaches 180 degrees, which is the transient stability limit or the rotor stability limit, and accordingly set up the relaying so that we do not reach the limit in the system. So essentially this is the critical fault clearing time calculation that can be used to determine what is the relay speed or the protection speed that must be used in order to keep the system stable. So I'll go ahead and open up the relay, enable it. It's already set up with certain amount of clearing time. So I'll go ahead and perform my calculation again. And this is where another capability of the program comes into play, where the fault is just initiated and the protected devices automatically detect the fault, and based on the characteristic the program automatically takes action, opens up breaker 11 and 9, and essentially is clearing the fault. So as we step through time and see further information, we can see the voltages are fairly stable, but we can visualize this again through our plot, relative angle and speed. So we can see that, yes, indeed, the fault was cleared in the correct amount of time, and the system appears to be returning to a stable limit. So this is typically what we would do inside ETAP as we model the electrical system. We perform standard system analysis such as power flow, fault analysis. We can also go into the coordination mode, place a fault on this transmission line, and based on the characteristics, once again, the program can tell you which are the devices that will clear the fault. And we can go to the transient stability module and place faults or take various actions and understand the electromechanical stability of the system. So typically the steady state calculations are done within ETAP. The dynamic electromechanical calculations are also done within the ETAP program. But then when it comes to the transient, fast transient calculations, the electromagnetic calculations, such as switching transient, insulation coordination, surge arrestor sizing, lightning surges, those are typically done in electromagnetic transient software such as EMTP-RV. So we have essentially collaborated with EMTP-RV in 2014, and both companies have announced an interface between ETAP and EMTP-RV software, which will essentially allow you to perform EMTP studies as a module inside ETAP. So the basic goal is to provide a platform that gives you greater analysis capabilities, especially when you're dealing with power system transients in the electromechanical domain and in the electromagnetic domain, using one network model and without duplicating the data entry effort. So with that, I'm actually going to pass the presentation over to Emmanuel from EMTP-RV, who's essentially going to walk you through the data exchange interface between ETAP and EMTP-RV and show you some of the capabilities within EMTP-RV software. So with that, Emmanuel.
Good morning. Good morning, everyone. My name is Emmanuel Rutovic. I am EMTP-RV application engineer at PowerSys France, as you can judge by my accent. PowerSys is a worldwide editor of the EMTP-RV software, and we are extremely excited by this collaboration with ETAP. First of all, we would like to sincerely thank our friends from ETAP for this great opportunity. And as a reminder, I would like to start my presentation with an overview of the different types of power system software that exist on the market. As you know, short circuit and load flow calculation that you perform in ETAP are calculated at the power frequency at 50 or 60 Hertz. It allows extremely fast and precise calculation, even if you have an extremely large network. ETAP can also perform electromechanical stability studies. They use the same power frequency model to calculate the electrical network and have a dynamic solver for the simulation of machines and the simulator and the simulation of controls. This brings extremely fast and precise results, even with extremely large network. EMTP stands for Electromagnetical Transient Program, restructured version. That means that we want to analyze what's happening below the milliseconds. We want to simulate fast transients. We want to analyze, for instance, switching transients. What's happening when I am energizing? What's happening when I am energizing lines or when I'm energizing the transformers? What's happening when a line? What's happening when there is a fault on my system? I also want to simulate power electronics, and I need to have very good physical and detailed model of the power electronics. For instance, we have absolutely extremely detailed model of PV converters and wind converters and HVDC converters that can actually model and simulate all the details that you can have inside such a converters. Finally, we also want to simulate lightning stroke and to see the effect of a lightning strike on the power system. Unfortunately, for all of these studies, we cannot use only the power frequency representation of the network. Why? Because we basically need to have detailed model of all the equipment. We need to have detailed model of lines and maybe to see the propagation of a lightning stroke on the lines. We need to have detailed model of transformers to model the saturation of transformers. We also need to have a detailed model of cables and power electronics. So this is why we actually need to have another package which is actually able to represent all of these phenomena to run fast transient analysis studies. So here is a quick overview of the software. EMTP is a little bit like ETAP, but for fast transient analysis. It's a full-featured, all-in-one software that can run all these fast transient analysis. It's quite open, and you can actually connect the software with other third-party softwares like ETAP. It can simulate a large range of phenomena. And as I said, detailed model of machines, lines, cables, transformers, and so on. What are the key features of the software? When we talk about fast transient simulations, something extremely important is the solver. Fast transient simulations are kind of complex, especially if you have a very large network, and we claim that the EMTP-RV solver is actually the best that exists on the market. It can simulate in a second very extremely large network without compromising the precision, the accuracy of the system. Something extremely important in EMTP is we do have a log flow. Of course, EMTP is not a log flow software like ETAP, but we do have a log flow inside EMTP basically to initialize the time domain analysis. When we start an analysis in EMTP, we directly start from the steady state. If you compare with other EMT package, you will find that this is not the case in the other packages. Finally, the graphical user interface that we have in EMTP is kind of is very easy to use, and it's entirely scriptable. You can actually script everything in the software to create your own studies. We do have 4 options of simulation in the software. As I said, log flow and steady state. The main simulation option is the time domain analysis to simulate the transients. And we do also have a frequency scan. Frequency scan can be used to check if you have any resonance in your system or to design harmonic filters. What are the typical application of the softwares? Of course, the simulation of all kinds of transients, fast transients and also transient stability. EMTP is a great tool to perform insulation coordination. You can simulate lightning, switching, and pair resonance. And as I said, EMTP is excellent for the simulation of power electronics and facts converter. Now we'd like to have a look to the benefits of the software. This is basically a summary of everything that I just said before. I just want to add that we know that I'm sure that some of you are new to electromagnetic transient studies, and I just want to say that we are also organizing a lot of training, and we have a good technical support that will help the new users to actually model and simulate their network inside the EMTP. Now I would like to talk about this new coming interface, the ETAP EMTP-RV import tool. As Tanuj explained, the idea is that a lot of our users, a lot of the EMTP-RV users, they also have basically ETAP license. But when they want to perform a transient analysis, basically they need to create again in another software the same network, enter the data, model the network, validate the model, maintain the model, and this is a lot of work, okay? So we decided to develop a tool that will actually import directly the data of the ETAP design inside the EMTP. This is extremely easy to use. You basically just need to export an XML file from the ETAP interface, and in the EMTP you will simply load this ETAP file, and it will automatically create an EMTP-RV design. Finally, you can run a time domain analysis and analyze the results. I just want to jump inside the EMTP-RV and to show you how it works. Let's disable this. So this is the graphical user interface of EMTP. Like ETAP on the right, I have access to my libraries where I have all my symbols. And if I want to import ETAP data, I just need to drag and drop an import data tool here. I simply double click on the import ETAP data option and load an XML file. Here I'm going to load the 9-bus design that Tanuj just showed. So if it kind of reads the main parameters and the main things of the design, and then if I click on OK, it will load and create the design inside the EMTP. Here is the model. Once imported inside the EMTP-RV, I find all the lines, the buses, the transformers, the machines, and the loads directly modeled in EMTP. And for instance, let's say that we use ETAP for short circuit and for selectivity analysis. But now we want to perform a capacitor bank analysis. We want to check the overvoltage that we'll have on this bus when I'm connecting a large capacitor bank, and we want to make sure that the equipment that are connected to this bus are correctly sized. So let's simply add a breaker. I'm going to the switches library, and I will add a breaker to the system. And let's add a capacitor bank. So I'm going to the RLC library and add a capacitor. Let's zoom a little bit. Let's connect this capacitor to the ground, and we can rotate this breaker here to connect it to the bus number 5. Okay, so this capacitor bank is a 20 microfarad capacitor bank, and I want to connect it at 55 milliseconds. And I want the capacitor bank to remain connected, to stay connected to the network. Now I simply need to go to the simulation options. Here my time step is 100 microseconds, which is, I think, sufficient to simulate such transients. And I would like to run the analysis. Just click on the Run button. And exactly like ETAP, the simulations here are extremely fast, less than 200 milliseconds. Let's go in scope view. Scope view is the tool that we use to actually analyze the waveforms. It's included in the EMTP-RV package. And let's have a look to the voltage on the first 5. So here is the voltage that will come in the bus 5. And as you know, when I close the capacitor bank, it actually acts like a short circuit, and this short circuit will lead to a transient that appear here. And here I have access to the over voltage when I close the breaker. So this is a very quick introduction to the ETAP import tool. The ETAP import tool is still in development and will be officially released by the end of the year. So now I would like to introduce a few examples, typical examples of EMTP-RV simulation. I would like to show to you lightning analysis. Let's go back to EMTP. And let's open a lightning examples. We provide with EMTP a lot of examples and a lot of application guide to help you design your own system. Let's open these examples here. So this is a typical insulation coordination design. Here we have modeled a 765 kilovolt gas insulated substation. Here. And we want to simulate the backflash of a case. So we modeled an incoming transmission lines here. We modeled the CVT and the lightning arresters at the primary of the substation here. And we inject inside the shielding cable of the transmission line a 200 kiloamps lightning stroke. So for those of you that are not familiar with backflashover, is basically when the lightning strike is current is too severe, is too high, that the voltage at the top of the tower rise to a very high value, and this value makes the insulators flash over. So even though when the lightning hits the shielding cables of a transmission line, you can actually lose the transmission line, and this is what will happen in this case. So in this case, if I look at my simulation options here, I'm going to simulate with a time step of 20 nanoseconds, which is extremely small, but you will see that EMTP will simulate that within a second. So in order to have a good model of a design for a lightning analysis, it's extremely important to accurately represent all the physical aspects of the lightning. Of course, you need to have a very good model of the lightning source itself. Here we use a model validated by the SIGRE. We need to have very good model of the transmission lines in order to model the propagation of a wave on the transmission line, and also in order to model all the coupling between the phases and between the shielding cables and the phases. We also need to have a very good model of the tower that will accurately represent the propagation of the wave inside the electrical tower. Of course, we need extremely good model of surge arresters to model accurately how the surge arresters will limit the overvoltage. Now, when everything is modeled, we can actually run the simulation. And as you see, it takes less than 2 seconds to simulate such a complex design. And I can go back in scope view, sorry, and have a look to the waveform. So I remove the previous waveform. And the first thing I want to look at is the current that we inject into the transmission lines. So this is a typical lightning stroke shape. And this is 200 kiloamps lightning strike. This is really severe. This is really high. And maybe I can start to look at the voltage at the top of the tower. So here, we inject the current at this point here, the lightning current at this point here, and we look at the voltage at the top of this tower here. So as you see, the voltage start to rise a lot, and it will slowly go down to 0. If I zoom in here, I can see that I have this oscillation here that are nothing else than actually the propagation of the lightning stroke on the lines. Now I can actually ask my insulators if they tripped. So I go back to the signals, and in the control section, I have actually some signal generated by my insulators, that's my line tower insulators. And here I can see that one of the insulators actually tripped because the Boolean signal goes from 0 to 1. So what is the impact of this flashover? If I look to the voltage at the bushing at the entrance of this of the substation, I actually see that the voltage C after it flashovers goes slowly to 0. This is because one of the insulator tripped, and here we lost the phase. So basically, what we do in the EMTP is we vary this current here, and we check if we have back flashover or not back flashover, in order to get what we call the critical current limit, the maximum current value, the minimum current value that will bring a back flashover. And if I know this current value, I can calculate the probability to have a back flashover and to lose my lines. This is part of the insulation coordination process. Now we like to quickly introduce some other design in order to perform a statistical analysis with EMTP. Here I have a 220 kV network modeling the software, and I am again connecting a capacitor bank to this bus 1 here. But as you know, the capacitor bank energization over voltage is related to the instant when you close the breaker. So it's important to actually represent the statistical distribution of this closing instance. So in EMTP, I have the statistical option here, and I simply want to run a statistical analysis, and I want to run 50 analysis. And during this analysis, I will close my capacitor bank at different instances that has a Gaussian distribution. Let's run the analysis. It will be quite fast. It will last only a few seconds, even though we're running 50 simulations here. By the way, we can use the same statistical analysis for a lot of different parameters. For instance, the instance of transformer energization or cable energization. This allows you to quickly have a look to the worst of the voltage that can happen in your systems. So now the 50 runs are finished, and I can use this mplot tool here to load the statistical data and give me the worst of the voltage that I have. So here I will simply get the voltage on the bus of the capacitor bank, and I would like to have the over voltage in per unit. So now if I go in the bar mode here, I see for the 50 runs, the different over voltages that I have. I can also have a cumulative distribution function here. That means that it gives me the probability to have another voltage higher than a specific value. For instance, here I can read that when I connect my capacitor bank, I have 10% of chance to have another voltage higher than 1.3 per unit. And as you see, this is extremely straightforward and extremely fast in EMTP. Finally, the last thing that I would like to show to you is a ferroresonance case. Ferroresonance is very dangerous phenomena that can appear on power system, and that basically when a transformer is resonating with the cables, when the saturation of the transformer resonates with the capacitance, usually the cables. So this is a case of ferroresonance here, where we model 11 kV network. This is a distribution transformer connected to a 400 meter cables. And for any reason, the breaker here didn't close. Maybe we had a mechanical problem, and one of the three phases didn't close. So now I would like to run the simulation, and we are simply closing this breaker and energizing the cables on the transformers. And I can again go in scope view. Sorry. And back in scope view, I can have a look and I can analyze the voltage that arises at my transformer. It's loading the data. It can take some time. Let's load it again. Okay, here I can actually see that on the phase C, the phase which is not connected, I have some over voltages, and the over voltages reach up to 3 or 4 per unit. Basically, it's way higher than the BIL of your transformer, and your transformer may have a big problem here. So you can use the MTP to understand, simulate, and mitigate ferroresonance. I will go back to the presentation now, and I would like to conclude with just an overview of the EMTP package that we offer to you. EMTP-RV is actually a package that has 4 things inside. What we call EMTP-RV, which is the computational engine, which is the solver. Then EMTP works, which is nothing else than the graphical user interface. Scope view, which is the tool that we use to analyze and view the waveforms of the system. Scope view is extremely powerful, and you can actually create a lot of functions, a little bit like MATLAB, and see all the details of the waveform. And finally, the ETAP EMTP-RV import tool, the tool that we use to import ETAP data inside the EMTP-RV. This is, as I said, the ETAP import tool will be available by the end of the year. So thanks a lot to have joined this webinar. Now I would like to give back the lead to Tanuj. If you have any question, do not hesitate to send us email, and we'll be pleased to help you. So now we'll give back the lead to Tanuj.
Thank you very much, Emmanuel. And as Emmanuel mentioned, the interface essentially between ETAP and EMTP-RV will be available with ETAP 14, which is to be available end of this quarter, beginning early next year. That's essentially the time frame. The tool essentially allows you to take the best of both worlds and migrate them together into one common platform, so you can essentially build the network model inside ETAP, perform the basic analysis, including power flow, fault, coordination, dynamic stability, and then for advanced studies such as fast transients, you can essentially migrate the data over to EMTP-RV without losing any fidelity, without losing any information. All the impedance data is essentially transferred over, including the machine models are mapped together. So you can essentially enter additional information that's required for doing electromagnetic transients and then start performing your calculations. So significantly cutting down the engineering time for advanced studies. So the ETAP and EMTP-RV is available as a package. You can essentially purchase the ETAP license together with EMTP-RV and with another third component, which is the actual interface or the bridge between the two programs. That also includes 1 year free upgrades and user support. So with that, I would like to thank you for attending today's webinar. As a reminder, our next technical webinar is on ETAP AutoStar. AutoStar is basically a new module being included in the next release of ETAP for automatic coordination and protection evaluation. This capability automatically detects zones of protection and evaluates whether you have sufficient protection and coordination in your system in an automated manner, and comes back and gives you feedback via graphical and tabular views. So this webinar is coming up in November. These are essentially the two different time frames you're able to watch this webinar. So please feel free to register on our website. The last webinar for 2014 is our short circuit result analyzer, which is on December 10th. This webinar is highlighting the short circuit analyzer, which is similar to the load flow and the arc flash analyzer we previously released with ETAP. So it's a very good time-saving feature that compares and filters various short circuit reports in one single tabular display. So you can take multiple scenarios, multiple fault calculations, and then essentially ask the program to give you the worst case condition in a click of a button. So again, significantly saving you a lot of engineering time as you do your system analysis. Once again, if you have any questions about this webinar, if you require any additional information, technical information about ETAP and or EMTP-RV, or have any pricing questions, please feel free to email us at sales@etap.com. We will be staying online for the next few minutes, and we'll be pleased to answer any questions you may have regarding today's webinar. You can ask your questions once again using the question pane located on the GoToWebinar control panel. And once again, I would like to thank all of you for joining us for today's webinar, and we look forward to seeing you at the next one. Thank you.